I do not want to mix up this element x plus this ideal, and I call this J, not I. And so F has the elements 1, 0, 1, 2, J, and 2J. 2J is the same as minus J. 1 plus J, 1 plus 2J, which is, so to say, the complex conjugate to 1 plus J, and then 2 plus J, 2 plus 2J. Now, the idea of Dixon was to change the multiplication in F to a new multiplication circle to obtain the near field which we are dealing with, or which we want to see. The additive group is not changed at all, of course. And again, I want to remind you how C, the complex field, is constructed and how our F is constructed. F are the complex numbers modulo 3. Now we form a subgroup of the multiplicative group of F, subgroup of squares. This is a subgroup of index 2, and the mapping from x to the 3 turns out to be our automorphism of F. This is clear because we work in over Galois field with 3 elements in this is an automorphism of F of order 2, and it maps the squares to the squares. And if one wants to build up a multiplication table, it's useful to compute the squares and the third powers of the elements. Well, 0, that's not interesting, and 1 as well. And one can see that in the multiplicative group of this this Galois field 3 square, that one is 1, 2, and J, and J2, 2 times J. These are the squares. So U is the subgroup. U is 1, 2, J, 2 times J. And now the multiplication, the new multiplication circle in N is defined by, well, just for completion, 0 times B is the old multiplication is 0. A times B is the old multiplication if A is a square, and it's A circle B is a sigma B in case A is not a square. And now, yeah, okay. No. Now we take page 33. Here you have now the example of Veblen-Wedderburn, but translated into the language or into the concepts of affine geometry. Wedderburn worked with a projective plane. Clay translated this into a fine in a fine concept. It's much more suggestive. We want to show that the affine plane over this Higgs near field of 9 elements yields an affine, that this affine plane is not the Sargasian. Okay, we start with a point and 3 lines for this point. That's P. P, there is a small mistake. P should be J2. 2 is the same as -1. And this is incident with 3 lines, L1, L2, and L3. And we form a triangle by choosing points Q1 on L1, Q2 on L2, and Q3 on L3, of course. And the line combining Q1 and Q2 is called L4. And yes, Q2 and Q3 is L5, and Q1, Q3 is called L6. We choose L4 to be the, so to say, the x-axis, and L5 to be the y-axis. And then we must determine certain coordinates. We get we can choose Q1 to be 0, 1, Q2 as 0, 0, the origin, and Q3 as 1, 0. Now, and now we must find a triangle where a triangle with the corners R1, R2, R3, R1 on L1, and so on. And the corresponding sides should be parallel. If 2 of the corresponding sides are parallel, the third must be parallel as well. This is what we would have to prove it if we would claim that's the Sargasian. And the point is now that this L9 should be parallel to L6. And if you, I give you a list of what we know on L5, L6, L7. L7 infinity 2 plus 2j. That means we have a parallel to the y-axis. L8 0, 1 plus 2a 2j means we have a parallel to the x-axis. And after some fiddling and some computation, it turns out that L9 and L6, which should be parallel if this axiom would be valid. This is not the case, but we have a common point S 2j, 1 plus j. This is on L6 and L9. So L6 and L9 are not parallel, they have a common point. And so this arc axiom is not valid. The geometers have funny notations. Arc A means A is the Sargesian, and if it's a capital A, it's the great axiom, and the small restricted axiom is written with a small a. Now I would ask to look at page 35 before 34. I made the numbering thoughts. Do we have 80? Oh, yes, yeah. You see this diagram. If you, yeah, when you are given a geometric structure and you want to identify this with, for instance, a affine plane over a certain field or near field, or I don't know what. The technique is to identify the elements of the structure to be obtained with the points of a line, and then you have to define addition and multiplication on this line. And here you see if you have the normal addition on the middle line, you can easily construct S plus T. And if you have the small, the Sargesian axiom S plus T is uniquely defined. You see here, if you do this, if you would take another line as starting line, then you would get the same addition on any line you consider. And a similar, this is here the small, the Sargesian axiom is sufficient. The small Sargesian axiom guarantees that we have a well-defined addition. In order to construct a multiplication, we need the Sargesian axiom. Look at the line, the two outer lines, then you may construct from a S and the T, the ST, and the middle line and the parallelity of these sides of the triangles guarantees that this ST is uniquely defined. Now in 34, we have a Pappos figure. If you consider the upper ray, you see how you can, from 1 and T and S on the lower ray, you can construct S times K, S the left factor. Conversely, from 1 and T and S on the lower line, you can construct T times S. These are the laws of proportion. And TS and ST is equal if and only if the two lines, which I marked with kind of an equality sign, are parallel, and this is exactly the axiom of Pappus. When Veblen and Wedderburn wrote their paper, they proved independently that Pappus is violated and the Sarg is violated. In the same year in which Dixon constructed his near field, and 2 years before Veblen and Wedderburn wrote their paper, Hessenberg proved that if a affine plane or a projective plane, if such a plane satisfies Pappus, it satisfies the Sarg. So Veblen and Wedderburn could have saved a lot of work if they had known Hessenberg's theorem, but they obviously didn't know it. Now, 36. In order to have a good feeling for Frobenius groups. Frobenius group is a semi-direct product of a group with fixed point free automorphism group. I think we should keep these examples in mind. In the context of permutation groups, Frobenius group is defined as a transitive group on a set omega with minimal degree m minus on a set omega of m elements with a minimal degree m minus 1, which means the stabilizers of one point must have the minimal degree, and if you take in G alpha the stabilizer of beta different from alpha, this must be 1, because this would be m minus 2 transitive, and the minimal degree of this group is m minus 1. And Frobenius introduced these groups and proved by means of representation theory that the set of the irregular elements in this group, together with the identity, is a normal subgroup. The real, this is done in representation theory by showing that R is the kernel of a suitable homomorphism of the group in question. And that R must be normal if it is a subgroup, that's clear from the, relatively clear from the context, but that it is a group at all, that this is the point. In the context of abstract groups, we assume that R has a class of subgroups each of which is has intersection 1 with its conjugate. Of course, if the conjugate is the same, conjugate of H is the same as H, then this doesn't apply. And then you take from the group G away all the union of the H's and add the identity, and this must be then a normal subgroup. We call R the Frobenius kernel and H Frobenius complement. The first two examples are pretty simple. G, the symmetric group on 3 elements, which is the smallest group, not commutative at all. This is a Frobenius group. The Frobenius kernel is the alternating group, and any one of the transpositions generates a cyclic group of order 2 and is a Frobenius complement. The second is also very simple. You take an n-gon, a regular n-gon. On the picture, I have a 5-gon pentagon. It's important that n be odd, then the group of rotations and reflections turning over of such a figure is a Frobenius group. The Frobenius kernel consists of the rotations, and any reflection on an axis, the axis must go to one of the, since n is odd, must go to one of the corners. This is a class of Frobenius complements. Much more interesting, I think, is the following. If K is a field with at least 3 elements, we consider the triangular matrices with determinant 1. Triangular 2 by 2 matrices, and yeah, okay, you must have in the main diagonal a non-zero element Q and its inverse, and then in the right upper corner some other element of K. In this case, the Frobenius kernel consists of those matrices with 1s in the main diagonal, and the Frobenius complement consists of the diagonal matrices in the narrow sense. They have Q and Q minus 1 in the main diagonal and 0 elsewhere. Now, a few examples. The first is, yeah, it's a kind of negative example. It shows that one shouldn't deal with too small structures. If you take the Galois field of 5 elements, then the multiplicative group has 4 elements, and the multiplication by 1 and by 4 forms a cyclic subgroup of the multiplicative group, and by multiplication from the left, it yields a fixed point 3 automorphism. So if you apply these multiplications to 1, then you get the 2 orbits 1, 4 and 2, 3. And now if you form the multiplication table in such a way that you just write these these orbits in this order, then you will see that these 1, 4, they form a they form a subgroup of and also the 2 and 3. These lines is repeated because the multiplication by for instance by 4 and by 3, means that you apply the same element of phi on the element 1 or 4 and the same 2 and 3. So you get this very I would say nice multiplication table, but it shows that if you form the blocks, you get 10 blocks, and 10 is 5/2. So all the two element, all the two subsets of the Near-ring constructed are blocks, and this is not interesting. R would be 4 in this case. And since the number of elements in this phi is the same as the number of equivalence classes, we have only 2 equivalence classes, and this is by definition not planar. So that's nice and simple, but it doesn't help too much. Yeah. Now, much more substantial is the example which we considered. We start with a Galois field of 7 elements and use as a fixed point free group of automorphisms the cyclic subgroup of order 3, cyclic subgroup of the multiplicative group of Galois field with 7 elements, and we know we have these 2 basic blocks, 1, 2, 4, and 3, 6, 5. And by the same argument applied as before, we see that the structure of this cyclic group of order 3 is imprinted on these elements. By suitable interpretation of these elements, you see that's the multiplication table of a cyclic group of order 3, and the same is true with this orbit, and that this scheme is repeated. That this is due to the fact that multiplication from the left is applying a certain automorphism, and we apply the automorphisms. Klee introduced 1 subcircle, 2 subcircle. That means multiplication in the usual sense from the left, which induces fixed point free automorphism. And it's very easy, we have this, it's very easy to obtain the blocks. You just have to add the elements of the additive group, the small, practically the smallest positive residues modulo 7. This plus 0 doesn't change anything, and then This is so, I call this B0 up to B6 and B7 up to B13. We have V equals 7, K equals 3, B14, and this is substantial. Substantial is smaller than 7 over 3. You have only 40% of the 3 subsets of this 35 of all 3 subsets. R is 6. Okay. Now we come back to circularity. Let phi n be a Ferrero pair, and from phi n we derive an integral planar nearing. It's, as I pointed out, it doesn't make much sense to leave a.
Excuse me, Gerhard, I need some time to change the.
Oh yeah, sorry. This 39 and 40, which I need now for the rest of the time.
Oh, excuse me, I'm still looking for the correct.
For page 39, please.
Okay, now we have it. Sorry that it took so long.
Ah, yeah, very good, very good. We start with again with a Ferrero pair, and from this Ferrero pair, phi n, we may derive an integral planar nearing variant. It's reasonable to choose it as integral, and a balanced incomplete block design NB or B star epsilon. You remember this small diagram. We can go from the Ferrero pair to the IP nearing, or directly to the balanced incomplete block design, or from the nearing to the block design. Now, what are the parameters of the balanced incomplete block design which we obtain? No matter, we have here a certain liberty in constructing the IP nearing, because we have a liberty to choose representative elements in the orbits. Well, it's clear the number of points is n, and the number of blocks is the number of these n star A plus B. And if we remember this result, which is relatively easy and which I didn't prove, then we see that this must be v minus 1 times v over k. Every block contains k elements. This means, and this is the number of points which we, for A we have y minus 1 choices, and for B we have y v choices, v minus 1 and v choices over k. Now k is of course the order of phi, and this is the order of one of these basic blocks, or and if you just meditate on how multiplication is defined, you see that the number of elements of phi must be equal to the number of to the number of these equivalence classes. If we say, if the equivalence classes are on n star, and if we take n, we have one more equivalence class, this trivial equivalence class. We have then this minus 1, and n star is n minus 0 in this case. Now we have these relations in the balanced incomplete block design, which I mentioned before. So if we have V, B, and K, V, B, and K, then we can compute R. This must be V minus 1. And if we take the second equation, we have lambda is equal to K minus 1. All right. Now everybody knows, or almost everybody knows, there are infinitely many primes, and if you take the Galois field of a prime element, you can construct, as we showed, quite a few finite integral planar near-rings. And so we should be happy to see that we have many circular near-rings. But it turns out that if we have a finite integral planar near-ring and we want it to be circular, we must have a certain restriction on K. This itself doesn't make the thing circular, but we have this restriction. K less or equal than 1/2, 3 plus square root of 4v minus 7. As above, v is the number of elements, a number of points in N. K is the number of points in such a basic block. Now, N has, how can we see this? N has v minus 1 circles, and each of them contains k k points and k over 3 subsets. Hence, yeah, we have this equation. Hence, no, hence we will have v times v minus 1 over k times k minus 1 times k minus 2 over 6, 3 subsets of n. And the left side of this equation may be reduced to v minus 1, v minus 2, k minus 1, k times minus 2 over 6. These is the number of 3 subsets of n, which belong to circles. Now, each 3 subset belongs to at most 1 circle. We have v over 3 subsets in n. Consequently, we have this inequality. The number of 3 subsets in blocks must be less or equal than v over 3, which is v minus v times v minus 1 times v minus 2 over 6. And now we have to, v times v minus 1 may be cancelled, also the 6, and we get 3. We get k square minus 3k plus 2 is less or equal to v minus 2. We form this to a complete square. So k minus 3/2 square is less or equal to v minus 4. This 2 comes to the other side, plus 9, 4. So we have 4 times v minus 7 over 4. We take the square root. We use here obvious laws of monotony. So we get k is less or equal 1/2 times 3 plus 3 plus this square root v 4 times v minus 7. And of course, since k must be an integer, we can take the this bracket. This is the greatest integer less well, did I mention this? No. These square brackets with x in these square brackets means the greatest integer less or equal to x. So that's a small reduction. Now, as we know, there are infinitely many primes. So and all these primes yield a field, and all these fields yield many possibilities of forming a Ferrero pair, and each Ferrero pair yields several planar near-rings, and hopefully we can have circular planar near-rings. Now, it turns out that the bound given in B seems to be conservative, as the numerical analysts say. It's very cautious. It's opposed to sharp. But Modisette, a student of Clay, has shown that the bound in B will be attained in infinitely many cases. So it's not in yeah, maybe that we could do much better. We can have a much greater K, even in a circular planar nearing, but for infinitely many cases, this bound is sharp. All right, in Clay's book is a series of results on the geometry of integral circular planar nearings is presented under the headline Geometry of Circular Planar Nearings. But this is a kind of geometry which has not much to do with geometry in the usual sense. I decided that I will not go into these details, but I have to mention that Clay provides a table with useful parameters, not the usual the parameters we had here for balanced incomplete block designs, but it gives a list of primes and how you can, from the Galois field with prime P with P elements, how you can how you can construct in various ways a planar nearing, and hopefully it might be a circular one. The list of Clay considers the primes from 13 to 997, and of course, using computers, you can do much better. But all right, if you feel you would like to construct these such nearings, or if you have to have a balanced incomplete block design, look at Clay's book, pages 62 to 64. This should be enough on planar nearings. I thought it reasonable to start with planar nearings in this course, because the course in winter ended with this very fine block design built from from a planar nearing of 7 elements. I would like to make a big line and start a different type of nearing theory under the headline Nearings of Group Mappings. And we go, so to say, to the other side. We consider a group, not commutative, and mappings of this group into itself. This leads to general, or in the interesting part, to zero-symmetric nearings. And it's a question of how to make the notation. They will have the same axioms as so far, and we then start how we can how we can describe the structure of such nearings, and this will lead to various concepts of minimal groups on which a nearing act, and various radicals. And then more at the end of the semester, I hope to present certain results on general radical theory as applied to near-ring theory. And there is also a type of near-rings which are called distributively generated. They are very close to varieties of groups, but this is, well, that's to be done in the future, and I would like to close here.
Well, thank you very much, Gerhard. So we will meet again next week at the same time.
Yeah. We meet again next week.
Yeah.
Today is the 19th, so it should be the 26th.
The 26th, if everything works out fine.
Yeah, we do hope. We do hope everything will work fine. Hope to see you again.
So
at least
see you again next week. Bye bye. Thank you.
Bye.
Bye.